Hello, we are reducing drag on skiers. I'm John Erdman. With me is Ryder Hoffman, Isabella Schuchart, and Liam Rochlow, as well as Chris Albrecht. Today we'll be going through our presentation of our work throughout the semester.
Hello, my name is Chris Albrecht, and I will be talking about the background information for our project. The drag force a skier experiences depends on their riding position, and we wanted to test that. The drag that the models experience was measured by the force transducers that are in the wind tunnel. We also obtained this data from the wind tunnel using LabVIEW, and we were trying to see what position produces the least amount of drag for our project. Hi, I'm Chris Albrecht, and I'm going to be talking about our test procedure today. So first off, we had to design and print our 3D models, and then when we had to figure out how to mount the models into the wind tunnel, so we glued a piece of wood on the bottom and drilled 4 holes through the skier and wood in order to put bolts through and mount it in the wind tunnel. During the test, we used LabVIEW to record the data, and after each test, we changed the angle of attack, and then for each model, and then switched the models and repeated the steps.
Hi, my name is Liam Rochlow, and I'll be quickly running over the test equipment that we used. The equipment that we used in order to run this test was the 3D printed models, of course. We had 3 models that we had printed out to test the 3 different positions of the skier. We also used the wind tunnel in the 401 lab. We used a wooden base to mount the models to the force plate in the wind tunnel. We used a force transducer along with the LabVIEW software on the computer next to the wind tunnel. And we also used a few bolts, a drill, and epoxy to actually mount the 3D models to the force transducer. For the experiment costs, for our procedure, we didn't have any costs due to all of our resources being available to us, including Makerspace, where we have currency to print our own materials, as well as a machine shop, which is free to students at Clarkson. And then we used a few scrap materials from the Design Build Fly program here at Clarkson.
Hello, my name is Ryder Hoffman. I'll be going over the risk assessment of our experiment. So our experiment in general had very low risk. Our only risk involved in our experiment was the wind tunnel operation. So that was minimalized by wearing safety glasses and ear protection while operating the wind tunnel. And then in order to prevent any of our model breaking off in the wind tunnel and causing damage or any sort of thing like that, we removed any possible break or parts that could potentially break off from our model. So we, as you can see in the image below, we took off some of the skis and then the ski poles just because they were a little flimsy and we did not want them to break off in the wind tunnel. Hello, my name is Ryder Hoffman. I'll be going over our wind tunnel results. So as you can see in the 3 figures, we have our positions shown mounted at 0 degrees, -3 degrees, and -6 degrees. And then so for our drag for the positions while at 0 degrees, our position 1 had the lowest amount of drag the whole entire time through all the velocities, followed by position 2, and then followed by position 3. And for -3 degrees, it followed the same trend where position 1 will had the lowest amount of drag, followed by position 2, and then position 3. And for -6 degrees, it also had the same result of our tucked position 1 having the lowest amount of drag throughout, followed by our half tucked, and then our standing straight up design.
Hello, I'm John Erdman. So we also calculated the coefficient of drag for each model. So as we can see, the drag coefficient formula is listed above, as well as the variables. The most challenging part of this was determining the area for each skier. So we use kind of the face area that the wind would be contacting the model at to use that as our area, and then the velocity was calculated in the wind tunnel, and then the drag force was taken from our data. So as we can see, that position 1 yielded the least amount of drag for its drag coefficient, and then followed by position 3 having the most, which is also comparable to position 2, which had similar values.
Hi, I'm Isabella Schuchart, and below are the two figures from the ANSYS CFD analysis. To the left, you'll see our geometry uploaded into ANSYS Workbench. On the right, you'll see the volume mesh used to take the data. Hi, I'm Isabella Schuchart, and in order to use data from ANSYS, I created a SOLIDWORKS file for each position, adding a rectangular box around our skier for boundary conditions. The ANSYS data differs from the small-scale wind tunnel model because it is true to real-world size. In order to get the same data, we divided by 8 since our model was an eighth of the size. The symmetry plane in ANSYS cut the athlete in half, so the final drag needed to be multiplied by 2. The inlet condition looked at the velocity inputted speed in the z direction. The outlet condition commuted a pressure outlet. Each boundary condition was a wall of the outer box moving in the negative z direction. Theoretically, this would be snow. The skier's body was a stationary wall in order to calculate the drag of him.
Hi, I'm John Erdman. We also compared our wind tunnel values to our ANSYS values. As we can see, the error values are not too alarming. We have a few over 10%. This could be because the force plate in the wind tunnel was not accounted for in our ANSYS model. There was also could be an improper calibration of our force plate, as well as the noise from the force plate going into our LabVIEW data collection. But overall, we can conclude that this data from the wind tunnel is accurate, proving our theory of position matters in producing drag.
Lastly, we would like to acknowledge everyone that helped us through 401. We'd like to thank Professor Hoover, our TA Sayi, Owen McGuire for ANSYS help, as well as the entire MAE department for their help and guidance throughout the past 3 years that helped us use the equipment.